So I'm super happy to be here today. This is quite a big achievement for my team. We have been working on what I'm going to present to you today for the last 3 years. This is usual stuff in R&D, right? You prepare for quite a bit of time. I've tricked you all into this session, which you believe it's about AI. It's actually not. So sorry about that, just right now. My name is Florian. I'm a principal architect at Axelera, and I'm in charge of basically all things RISC-V. As usual in a startup, you wear multiple hats, so we'll help out with software, we'll do the architecture, and what I'm going to present today, we also design our own RISC-V course. So where am I coming from? Axelera itself is, or has been focusing a lot on edge AI applications. So usual things are running CNNs and doing object recognition, object segmentations for market segments like retail, robotics, security, and all the industry applications. And we have proven that this can be done with our Metis solution. This is the product that's in the market today. And I all invite you to actually take a look at the booth and see everything in action. And what you can see here on the bottom is a real Metis PCI Express card as it exists today. It's no mock-up. I'm very proud of that. But there is one catch. Vision, the whole CNN parts and the object detection is one thing. But it turns out that there is actually much more that needs to be running as part of a meaningful application. And this is usually, for like the example of a YOLO object detection segmentation pipeline that I took as an example here, capturing a camera input stream. You're doing color space conversions. Then you resize it because the network has been trained on smaller images. You quantize it. You make it appropriate for your accelerator to ingest. And this one is quite a bit of compute that we are currently doing on the host system. And I come to the drawbacks of that in a minute. And then there is also different applications, what we call mid-processing, but basically it means that you're chaining multiple neural networks back to back to achieve a meaningful application. So that could be region of interest detection, and then you do an object segmentation of a region of interest instead of the whole network. And then there is a whole lot of post-processing. So what you usually get out of these networks is a plethora of bounding boxes, and then your CPU or your host system needs to make sure that it only picks those or kind of collapses those to meaningful bounding boxes. And then you prepare it for showing it to the user, so you color it and so on and show it to the user. And what you can see, and we actually have quite a nice demo in our booth, is that for many of those applications, you're kind of what we call host bound. So the accelerator itself could run way more frames per second, but you're bound by the effective pre- and post-processing. And now you can say, okay, I bring my own GPU, and you bring your own integrated graphics, but then again, this increases your system price. And finally, you could say, yeah, I do everything on the host, but then you also do copy operations all the time. And PCI Express is quite fast, but then if you're doing like thousands of frames per second as we do, is not as fast. So we'll run into limitations there. So what is the solution? Obviously, yeah, just do everything on the chip. But we are an AI accelerator, as you remember. So what we think the solution to this problem is is doing our own custom design that accelerates those things. So when we were back in the days, 2.5, 3 years ago, as I mentioned, we looked at a couple of different options. So first option is you go buy a dedicated DSP IP. There's a couple of those out there. They have relatively good software support, but they come with the drawback that they come with proprietary tool chains. And then you choose a vendor, and then you build your own kind of software ecosystem on top of it. And that it eventually kind of locks you into this whole vendor, which is, for a startup, I would say, even like for larger companies, not my preferred solution, at least. Then there is embedded GPUs. You can embed a GPU on the chip. It is very good. It's programmable. Again, software support is relatively good, especially for things like image processing. But then, again, it comes with its own proprietary tool chain. You're locked into the vendor where you choose the embedded GPU. There's not a whole lot of GPU vendors that produce embedded GPUs. and then potentially also the performance that we've been looking is too low for the applications that we wanted to go for. And then finally, let's build everything from scratch. It's custom DSPs, everything designed from scratch. We'll probably get a really, really good performance, and it's tailored to these applications. You can even make it programmable. But then again, you're in front of an enormous amount of software work. You need to port your own toolchain, maintain your own toolchain, and finally, you're kind of accumulating depth, technical depth that you don't want to really carry around. So what we thought in Axelera is that RISC-V vector extensions are the solution to this. And what we have been building in the last 3 years is an extension to an open source core, which is CVS6. We call it CVS6V because it has been extended with the vector unit. And the vector unit we have been building offers 4K. So the design that we have been showing today is a 4K vector length. It's the embedded profile with up to 32-bit of element size and a data path length of 1024. We chose the much larger VLAN compared to the DLAN because we have a very relatively weak but low energy, low power CPU, but then we keep the vector unit busy with the long vectors. And the problems that we are looking at are relatively long, and so we can keep the unit busy. And then we have a couple of interesting design choices that we brought a very large scratchpad memory where we are doing dedicated data movement in and out of it. And that is all controlled by CVS6 that we also have enhanced a bit for the application in mind, but it's largely what has been available open source so far. So you get your normal L1 caches, it's an in-order design, and yeah. This one really offers us great programmability. We have a good emerging tool support. It could be better, and it will be becoming better, and we are also working on it, especially in terms of available software. But we are building on a foundation that is there to last, and that we can actually build a software stack up. Because the software stack, after all, we are very hardware focused here, it is by far the most expensive part of the product. And the extensions themselves, we don't have any custom extensions for this first generation of vector unit. Is really RVV 1.0. And then finally, what we are envisioning is that we are benefiting from open source software that is building on RISC-V vector extension, but we are also planning to contribute back all the kernels and image processing that we are building upon this. And with that, I'm very happy that this CPU that we have been designing for the next generation, we are introducing Europa, which is the next generation of edge AI processing. It offers way more performance than the previous generation, up to 629 TOPS in a power envelope of 45 watts. And we have increased the core count from the last generation, which is Metis, to Europa by 2x, and came up with much higher memory bandwidth and larger memories. You can imagine the workloads that are coming towards this design require a lot of memory. And the new thing, the really new kind of architectural things are these 2x8 RISC-V vector cores that I've been showing, which are meant for pre, mid, and post-processing. And then finally, we also including a H.256 to 64 encoder, because then we can bring in the compressed video stream, decode it, process it, analyze it, and show it to the user. And what it effectively means for our customers is that they can run more concurrent streams now on Metis than on Europa than on Metis. We offer more frames per second, and this all on a less powerful, that means cheaper host system. So what we call the programmable vector engine, it is made of the building block that I've been showing you before, the CVS6V. We're bunching up 8 of those into what we call a PVE, a programmable vector engine. Each of them comes with 2 megabytes of L1 scratchpad memory and a dedicated data movement engine that is meant for moving 2-dimensional data structures, images and videos into these scratchpad memory. We have 2 of these PVEs, so in total 16 cores made for pre- and post-processing. And the vector engine inside the CVSX has very high throughput, fine granular access towards the memory. And then their DMA provide relatively high throughput, but more granular access to the system memory, so DDR, backing DDR memory. And CVSX-V has relatively low performance in comparison to the 1024 bits of bandwidth per cycle to the memory. Compared to that, the CVSX-V itself has way, way less. And we can offload 1 instruction per cycle. We're operating at 1.2 gigahertz. We're quite proud of that, so we pushed it quite a bit. The 8 hardware tracks that I mentioned, and the custom data movement. So roughly, we will be announcing way more performance figures in the next months when there's more detail on Europa. But I still have a small sneak peek on what the PVE engines support. And that is, we now are able to support on-chip 16 Full HD streams at 30 FPS in pre- and post-processing. And this one scales with the resolution and the frames per second. And roughly speaking, as this is still like a technical conference, I needed to include a chart here. We have the pre-processing where we usually, so what we did so far is dedicate 1 PVE cluster into the pre-processing and 1 PVE cluster in the post-processing. And you can see that the pre-processing, the color conversion takes quite a bit of time. And then the post-processing is quite the workload with the non-mask suppression, which is still for the vector, it's quite an annoying kind of workload. So in pre-processing, we would even achieve way more than the 16 Full HD streams. But yeah, that was the target basically. And in post-processing, we are roughly at the 20 streams, Full HD streams. So we're even kind of exceeding the target that we have set ourselves for these PVE clusters. And just to kind of put this a bit into comparison in what does, like for the example, this compared to real-world hardware that is available today. So we've run the same, we've run the CUDA non-mask suppression on the same kind of problem sizes on a mobile GPU, 4060. Okay, it's not the newest generation. Back in the day, it was the newest generation. And we outperform with a single core. So we have 16 of those guys. With a single core, we outperform the entire mobile GPU. And with that, just kind of briefly touching up on the programming model, the short gist of this slide is we're not changing anything on the programming model, so we are building upon what we have been doing for Metis. But now, with the new generation, you get the possibility to actually offload pre- and post-processing kernels as well. And we eventually, most likely, will also open this up for custom applications. So just briefly walking you down how the software stack looks today. So what we have is an application framework, which brings all these kind of nice frameworks that you would be expecting. So GStreamer pipelines, so that you can build your vision pipeline. The TVM compiler that is doing the compilation of the neural network, and then the runtime based on level 0, which is an open standard API. And then the custom user space and Europa kernel driver that are doing actually the offload towards the PCI Express. And as I said, we're not doing anything now, but might be in the future looking into more kind of fine-grained programming model with OpenCL. But this is purely up for the air. So how does the Europa product line fit into the whole strategic vision of Axelera? And what has been here is, so we love moons, in case you didn't notice. So we have the Metis product, which is kind of the edge product that we are showing today. Europa that I've been announcing today. Correction, it was actually announced yesterday, but I am announcing today that we are using RISC-V quite for a bit of compute in there. And then what has been also been announced that Axelera is partnering under quite a bit of European funding in the DARE project towards data center chip. So summing up, so what's the roadmap and availability? So we haven't exact availability date. Will somewhere next year. It will come in a PCI Express form factor and offer you the 3 to 5x performance to the other solutions on the market. And with that, I think nothing left to say except for visit us at the booth. There is amazing demos, and we talk to our kind of customer success team there. And the demo theater, I think, is unfortunately over. It was in the morning, so forget about that. And then finally, from my point of view, we are doubling down on RISC-V. So if there's anybody interested or you know anybody interested, we are hiring actively for the position of an R&D engineer in the CPU section. That brings me to the end. Thank you very much. I think I still have 1:40 for questions.
In my understanding, it seems like there's an inherent conflict at the edge versus data center. The data center is basically a throughput machine. At the edge, actually, you should have a more focus on the scheduling for the efficiency instead of like a data throughput. So how, with the same architecture, you're going to deal with like both ends?
I think you're implying that we're using the same architecture, which I cannot really comment on. I think we haven't released anything on the architecture. We're for sure building on the same kind of technology, but we might be wiring up it a bit differently. That's all we can really say about.
Someone else?
Here in the front.
Just to make sure I understood, you still have like a dedicated image processing in the middle of the pipeline, right?
Yeah, so the CNN part is all kind of custom. It's more like going into the direction of what you call AME, basically in RISC-V lingo. Yeah, so that's the whole CNN part I kind of really left out today. There is also more that we'll be announcing around that one. We built the CPU component as a reusable piece.
But the CNN part is inside Europa? Or?
Yeah.
Okay.
Yeah, it's 8 times inside Europa, and then plus the post-processing and the pre-processing.
Thank you.
Okay, thank you.
Okay, thanks.